This is the video for Mod 9, Lesson 3A on similar triangle theorems. All right, so the goal of this lesson, we're going to be talking, the last unit or section we talked about dilations, so stretching and shrinking figures or creating similar figures. This section, we're going to start focusing on similar triangles and a little bit of similar polygons so we kind of understand what we're doing here. So the goals are going to be determining if triangles are similar, and it's going to be using one of our three postulates, angle, angle, side, 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 or side angle side similarity. And that's really, we're just going to be identifying similar triangles. Before we can start talking about similar triangles, we need to make sure we understand what it means for figures to be similar. And we saw this a little bit when we talked about dilations in the last section. So again, in order for figures to be similar, they're not going to be necessarily the same size. So we're going to find that the corresponding sides, or the sides that match up, are going to be congruent, but the sides that correspond are going to be proportional. So again, when we write that as a ratio, we're going to have a scale factor like we saw when we did dilations. So to give you an example, you might be given like a similarity statement, and this is saying ABCD is similar to MNPQ. And so when we look at how that's written, very similar to congruent triangles from Math 1, the order matters. So this is basically saying A pairs with M. This is saying B pairs with N. That C pairs with P. Again, that's the third letter. And then finally, D pairs with Q. So when we write this out, you might have to write it as just listing your congruent pieces. So angle A is congruent to angle M. Angle B is congruent to angle N. Angle C is congruent to angle P. And angle D is congruent to angle Q. The sides we're going to do in a very similar way. So you can see the first two letters are AB, the first two are MN. So I like to use highlighter for these. So AB and MN correspond. So we're not saying they're the same length, they just match up. We have BC pairs with NP. CD is going to pair with QP. And then finally, AD pairs with MQ. You might have to write a proportionality statement, so you would just write it as a fraction. So I know that side AB pairs with MN, and just when I write it, if I'm choosing values from this first figure to be written on the top part of the fraction, I just have to be consistent throughout. So if I list the top as AB, I have to list the second one as BC, and then I have to list in that order. So if I'm choosing like from figure 1 to be on the top, I got to be consistent for every part of the fraction. And so if they ask for a proportionality statement for the sides, you would write it as a series of fractions. Now we're going to kind of shift the focus to specifically talking about triangles, right? So they're still obviously similar polygons, but we don't need to have every single piece known to say triangles are similar. So I don't need to have all the angles listed and all the sides listed to say two figures that are triangles are similar. I can use one of these theorems, which basically means if I have a certain combination of pieces, I can say that they're similar. So our first one we're going to talk about is angle, angle. And so what this basically says is if two angles of a triangle match with two other angles, that's enough to say that the third angle obviously matches up because it adds up to 180. And then that's enough to say they're similar. So I don't need to know everything about the side lengths for this figure to know that they're similar, because I have two angles that match up. I have angle A and D, and I have B and E. So if we have enough information, we would say, if they ask if they're similar, we would say yes by angle, angle. And then our similarity statement, we can write a whole bunch of ways, but we have to write it in corresponding order. So like, for example, angle A is marked with one tick mark, so is D. So maybe I write angle A and D. I could see B and E, and then C and F. So if I call the first triangle ABC, I have to call the second one DEF. And not because it's alphabetical order, because that's how the angles correspond to each other. The second similarity postulate we have is side, side, side. So again, that's saying we don't need to know every single piece about for two triangles to be similar. If I have that all the sides are proportional, maybe I don't know anything about the angles, but I know all the sides, corresponding sides reduced to be the same fraction. That's also enough to say they're similar. So I don't need to know all 6 pieces of a triangle. So the way you would do this is if I had these values here, you could see my smallest side is 4. And my smallest length on the second triangle is 6, right? So BC and FE. I then can see, well, my longest side is 8. For the first triangle. My longest side is 12 for the second. And then I could see my middle pieces. So we're going to see if these are similar by making a series of fractions. So my smallest was 4. That would pair with 6. Is that the same as the 6 pairing with the 9? And the 8 pairing with the 12? So notice all the values from the top came from the same triangle. All the values from the bottom also came from the same triangle. When I reduce it, I get all of these, I get the same exact fraction. I get 2/3. So what that means is, yes, they are similar. They are similar by side, 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 because they're all the same ratio. My scale factor is 2/3. And if I wrote it as a similarity statement, I got to write it in a corresponding order. So, for example, I always think it's easier to work with the angles, but you could do either one. So I see angle A is between the smallest side and the medium length side, or just between the blue and the purple. And then you can kind of just match all your stuff up. So if I call this first triangle, let's say ABC, I have to call the same one in the same order. So if I did 1 tick mark 3 and then 2, 1, 3, and 2, so I have to call this one DEF. And again, it's not because it's alphabetical order, it's how they correspond. Our last theorem we're going to look at is side angle side. So this one says if one angle of a triangle matches with another, and the two sides that include that angle are proportional, then they're similar. So for example, I see that there is one angle that matches, and if I trace the angle, the two sides that form that angle are including, are the two sides that we're going to compare. So I could see 2 and 5 are the smaller ones. So I have 2 and 5. I have 4 and 10. Notice values from the same triangle are lined up. And I'm going to see if these reduce to be the same. They do. And so that would be enough to say these triangles are similar. So I only have 2 sides, but I have the angle that's in between them. So if I want to name this, if I call this one ABC, I have to name this one in the same order, and I'd go DEF. These next examples are looking to see if we have enough information to say they're similar, and if so, we have to state the postulate and complete the statement, kind of like we just saw a moment ago. So if I look at this, I can see I have all 3 sides given. I'm going to test then with side, 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 because I have all 3 sides. So if I pick this, I might say the 30, which is the shortest, pairs with not the longest, with the other smallest value, which is 84. I'm then going to pair maybe what would go in numerical order, so this would be 35. I'm going to pair that with 98. And then my last piece, I'm going to pair the 40 with the 112. If we reduce that out, we get 5/14. And we actually get that for every single one of these. So the answer is yes, they are similar. So you would say yes by side, side, side. similarity, you put the little similarity sign. And then if we call this first one DEF, so DEF, right? You can see D is between the shortest and the longest side. That would match with Q. And then the next one is if I name E. E is between the shortest and the medium length side. So that would be R. And then S. So we'd have to call it QRS. This next example is same idea, so we're going to test it if these are similar. You might not see it right away, but these are actually overlapping triangles, and they actually share an angle. So this is angle, we have JEF, and then we have a second triangle, JKL, right? So we have a big one and a small one. They're sharing this angle in common. And then we have two sides here. We know that this is 13. If the whole thing is 26, this other piece is also 13, because you do 26 minus 13. This whole piece is 22. And I can actually, if I want to redraw it, I can. I don't necessarily have to, but sometimes with overlapping, people like to redraw it. So this is really the same as if I had 11, 13, and I marked that. And JKL, 26 and 22. And so you can see we're going to be testing for side angle side. So 22 is the longest or the shorter one, so is 11. So if I do 11 over 22, do I get the same thing as 13 over 26? Both of them give me a half. So it ends up working out. And so the answer would be yes, these are similar. This would be by side angle side. And if I call this first one JKL, I'm going to call this one JEF. If you have questions, make sure you are trying the U-Try problems and then asking for help during class, signing up for T-Bolt time, or getting help in the center.